Lab 4 by Daniel Manuel. Introduction. In this lab, we will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The main model is cleared in GlowScript and shows the predicted motion of a spring and mass model in blue, overlaid with the actual motion of the spring and mass in red. Fundamental principles include the work-energy principle and Newton's second law. The system includes everything, and there is nothing in the surroundings. Therefore, in the energy principle, the work is equal to zero. Overall, the simulation was accurate to the actual motion in the experiment and only showed a slight deviation in the x and y direction. Formulas. The formulas used are the velocity update formula, position update formula, spring potential energy, gravitational potential energy, kinetic energy, and the formulas for delta E. Here are the initial conditions. In the top right, you can see the initial position for the mass, which is taken directly from tracker, and the initial velocity vector. In the top left, you can see two constants such as gravity and the spring constant. And then in the bottom image, computes the system energy, as well as defining the initial energy. Tracker analysis. To capture the motion in tracker, a calibration stick was set to the original length of the spring at 0.7 meters, and the origin was set to the base of the spring. Then a point mass was used to capture each frame of movement starting from frame 5. The data was also separated into X and Y and then put into a CSV file that was used in the program. Code analysis. Lines 78 through 89 define the initial conditions, which include the spring constant and relaxed spring length that are taken from the pre-lecture videos. Lines 91 through 95 define the initial kinetic energy, spring potential energy, gravitational potential energy, and total energy using the following formulas. Lines 107 and 110 define the initial energies. Lines 113, 116, and 119 calculate the spring and gravitational force for the net force. Lines 123 and 25 update velocity and position, while 128 through 130 update the spring S value and then L hat. Lines 136 to 143 calculate the change in total energy, kinetic energy, spring, and gravitational potential energy. Models. The following is an energy graph for the simulation. In blue is the delta K, in red is the delta U grav, green delta U spring, and orange delta E. Models. The graph on the top shows the mass x position in respect to time. The blue line represents the simulation and the red represents the experiment. The graph shows a consistent positive shift for the red model. The bottom graph shows the mass y position in respect to time. In the y direction, the model consistently overshoots when approaching negative 0.64 meters, which means the model would be returning to a higher point when compared to the experiment. This could be due to the fact that the mass of the spring is not taken into account as it is massless in the simulation. What does it mean? For your model system, is the energy principle satisfied? The energy principle is satisfied and can be seen because the change in energy should be zero, as there is no work being done in the surroundings. And as you can see on the graph, it remains at zero for the whole duration of the program. In the second question, we were asked to find the period of oscillation in respect of x and y. If you find the period of oscillation in respect of x, it is 1.633 seconds. But if you find it in respect of y, you get a period of oscillation of 1.520 seconds. The difference in this figure could be from the difference in different distances the mass travels in its respective axis. Since it was not released at a perfect 45-degree angle, the periods of oscillation will be different. That's all for Lab 4, and thank you.